Today we would be continue the same topic, that is line coding technique, basic line coding technique, and there we have learned the binary line coding techniques as well as the multi-level line coding techniques to be uh, one IQ, as well as the we have to learn the last one is the multi-transition line coding technique, that is MLT3 scheme, that we have started the discussion yesterday. So we will continue from this point. If we have the signal with more than the two levels, we can uh, design a differential encoding scheme with more than two transition rules. And one of the multi-transition techniques is the MLT3. So the multi-line transmission, the three level MLT3 means that there are the three levels actually. So schemes having the three levels like plus B, 0 and minus B, and three transition rules to move between the one level to the another level. What are these transition rules? These are the following. First of one, if the next bit is 0, there is no transition. If uh, next bit is 1 and the current level is not 0, then next level is 0. If next bit is 1 and current level is 0, then the next level is opposite to the last non-zero level. Okay, so these are the three main rules that we have to follow when we are going to implement the MLT3 scheme. So now we have to see through the diagram. It would be give you the more clear idea. So before going to draw the timing diagram, we have to be first of all learn how to draw the you can say state diagram or a transition state actually. Okay, so once you have clear this concept transition states in your mind, then it is easy to draw the timing diagram for any binary any pattern that is given to you in the examination. Okay, so if you have to see that what is the rule is that first is that if next bit is 0, then there is no transition. So whenever either there are the three levels I have shown, one is the 0, another is minus B, and last one is the plus B. So either you are presently at 0 level or minus B or plus B. But if the next bit is 0, you would be remains on the same state. This is the first condition. Second one is what? Next bit is 1. But here also that there is a two conditions maybe there, because there is a two different levels plus B and minus B. So you have to see that if you are at 0 or minus B or plus B, if the next bit is 1 and the current level is not 0. So first of all we have to see that if the next bit is 1 and current level is not 0, like minus B, you are currently or minus B or plus B, and next bit is 1, then next level would be what? That would be 0. So it is very simple now. Now the last one is little bit complicated. You have to be remember that statement. Now what is the statement? Last statement is that if next bit is 1 and current state is not 0, means they are talking about you are at 0 state and next bit is coming as a 1. At that moment, it could be the two output could be possible. What is the first condition? That the next level is opposite to the last non-zero level. So if your last non-zero level is minus B, so the next level is plus B. If your last non-zero level is plus B, so your next level is minus B. And that we would be verified through this particular waveform. This is the typical case of MLT3. If you have to be see that you have started the zeroth level, you are presently at the 0 level and next bit is coming as 1. Okay, so you are at a 0 and next bit is 1. Then which state you would be going to transmit? So for that you have to be little bit assume. Suppose last non-zero level is assume last non-zero level is minus B. This assumption you have to be write on the paper. Okay, assume the last level is minus B, last non-zero level is minus B. At that then and then only you can say that if next one is 1 and you are at 0 level, so you would be moved to the plus B. Okay, now come to the next point. When again you are at the plus B level, but next bit is 0, next bit is what? 0. So you would be remains on the same level as per the rule that is mentioned in the first statement. Okay, no transition. But now another next bit is 1 and you are next bit is 1 and current label is 0. Next bit is 1 and your current label is non-zero. That is plus B is here. Okay. So at that moment, the next state would be what? Next would be 0. Next label is 0. Okay. Then again 1 is coming and you are at the current state as a 0. So next level would be what? Opposite of the last non-zero level. So what is the last non-zero level? That is plus B. So at that condition you would be come to the minus B. Okay. And then again 0 is came, means you are on the same, there is no transition. Then again 1 is came and you are at the non-zero level. So you would be transferred to the 0th level. And again 1 would be came. So your last non-zero level is minus B. So you would be now shift to the plus B. So this is the way that you have to be draw the waveform timing diagram for the MLT3 technique or MLT3 scheme. Okay. I hope this is clear. Just go through once again and again. Take the you can take the screenshot of this so that the idea would be more clear. Okay. So once or twice time you have to be, if you read this statement and follow the transition steps, then you have to be easily draw this diagram. Okay. So in the examination they would be sometime asked that you have to be some binary pattern is given 10 terms and you have to be asked that you have to draw the unipolar NRZ, you have to be draw the waveform of the MLT3, you have to draw the bipolar RZ like this. So 3 or 4 depending upon number of marks, each would be 4 technique could be there for the 4 marks question, 6 could be there for the 6 marks question, or maybe from this topic they would be asked like that comparison of this all line coding schemes according to the different grounds like the DC component, bandwidth. There is a multiple characteristics are there. On the basis you have to be draw the comparison table. Okay. So this kind of a question could be asked. Now we have to be come to the one more problem that I have left out in the past. We will be discuss this and then we have to be shift to the unit number 5. Okay. So this question I have given to you. Derive the expression for the maximum signal to quantization noise ratio or for the sinusoidal input, message input, and waveform coding is to be done by the delta modulator under no slope overload condition. So you have to be define the conditions that would be no slope overload conditions, and you have to be find out the signal to noise ratio. Okay, and sometimes this question would be asked the half of them also, that some sinusoidal waveform is mentioned, the equation is mentioned, and you have to be find out the condition of no slope overload distortion. That is also what is the value of the amplitude of the signal, that would be no slope overload distortion. So we will be see that. So to solve this kind of the problem, this is very important problem is there. We have to first write the message input signal is what? It is sinusoidal. So you can represent a sinusoidal signal as xt is equal to a naught cos 2 pi f naught t. Okay. This is a naught is what? It is the amplitude of the signal. Okay. And this is a sinusoidal. You can define a cosine function, or as well you can go for the sine function as well. This is a better way of representation of this. Now we have to be take this maximum slope of the signal xt is given by this is, we have done some theory that the maximum slope of the signal could be possible, a message signal, that is dx of dt. For the finding of the slope we have to differentiate the signal. So the maximum value of the dx of dt, only amplitude part we have to be take, that would become as 2 pi f naught a naught. Okay. So when you have differentiate this equation number 1 with the time dt, you would be got this. Only amplitude I am talking about. Okay. So now to avoid the slope overload distortion, this is the condition that we have learned in the past in the theory, that delta upon a step size upon ts is should be greater than or equal to the maximum slope of the signal. Okay. So under this condition we have to be substitute the value of this maximum dx of dt. So you would be find that this would become delta upon ts is greater than equal to 2 pi f naught a naught. This is the equation number 2. This is the amplitude of the maximum slope of the signal. Okay. Now the amplitude of the signal is sinusoidal signal is what? You have to be just rearrange this equation number 2. You would be got the equation number 3, that is a naught is less than or equal to delta upon 2 pi f naught Ts. Hence, the maximum permissible value of the output signal power is what? It is P max, that is A square upon 2. We know that the power and the voltage is related with respect to each other in terms of square form. So A naught is a voltage signal amplitude. So it is A square upon 2. Okay. So it would become as delta square 8 pi square f naught square Ts square. This is equation number 4. Where there is no slope overload distortion, the maximum quantization error is plus minus delta. Okay. So this is the one of the condition that we have find out the maximum power, permissible power of the output signal under the no slope overload distortion condition. Okay. So this is generally up to this point also they have asked that what is the value of the maximum power for satisfy the condition of no slope overload distortion. If it would be asked like that, then you have to be limit your calculation up to the equation number 4, and it would be maybe of the 4 marks. But uh, if it is as the signal to noise ratio, it would be increased to the 6 or 8 marks question. Okay. So further you have to be see that. I hope all of you have noted down up to this point. Okay. So simultaneously, please note it down all the equations. This is very simple. No, and it is very important problem. Actually, it is asked in the past 2 or 3 times. Okay. Now we have to be go for the signal to noise ratio. For that, we have to find out the noise power. We have to be already find out the maximum signal power. Now we have to be go for the output noise power. Okay, quantization noise power. Now see that the mean square value of the quantization noise error, quantization error we have already calculated in the past, that is delta square upon 12. We have already find that. So here you can see that delta is the step size, and in the case of delta modulation, we know that the step size is fixed, that is plus delta or minus delta. So if you have to be see the overall length of the delta is the twice of delta. Okay, so it would be start from the minus delta to up to the plus delta. That means 2 of delta. That's why we have to be substitute here the value of the delta. Okay, for the avoid of confusion, some books has also mentioned delta is equal to they have also used these terms also as well. Okay, 2 delta. So you can arbitrarily assume this, but you have to mention on the answer. I have not assumed like that. I have just considered that delta is here twice of delta because we are talking about the delta modulation. So it is would be 2 delta whole square is what is 4 delta square upon 12, that is delta square upon 3. This is the mean square value of the quantization error. So the receiver contains the low pass filter whose bandwidth is set equal to the message bandwidth, that is W I have taken. You can take the F max as well also. So F naught should be less than or equal to W, that is the bandwidth of the signal. So hence average power of the quantization error is uniformly distributed over a frequency interval extended from the -1 upon Ts to +1 upon Ts. Okay, so we would be get the average output noise power in this way, that is WTS delta square upon 3. Okay, so you have to just integrate from -1 upon Ts to +1 upon Ts, and that is the sigma square del T. That would be got the equation number 6. WTS delta square upon 3. This is the average noise output noise power. Now once you have to be or calculate the average noise output power, then you would be easily find out the signal to noise ratio. So the maximum value of the output signal to noise ratio is what? T max upon average output noise power, that is WTS delta square upon 3. You have to be substitute the value, and finally you would be got the equation number 7, that is signal to noise ratio, output signal to noise ratio maximum value. Okay, so in this way this would become as 3 upon 8 pi square WF naught square upon TSQ. Okay. So this is a very important problem that I have just take it out in this session. Okay, and I have taken this solution from the book of digital communication written by the Simon Hacking Willy publication. So that is also a very good book that I have maximum time refer for this chapter, or you can refer the top selling book, that is also a very good book. That is also the backbone of this 4th unit as well as for the 5th unit as These two books would be a backbone of the fourth and fifth unit. Okay. Okay. Now, so we have to become to the end of this unit. That is, you have to be see that these are the reference books are that I have referred for this unit. That is Top Selling, then Simon Hacking that I have talked about. These two books are the again I am saying that this is the base. But if I have to say the textbook, Bernard Sklar, it is also a very good book for referring the digital communication. Okay, so all three are the good book, and this is the Berhaus Porogen book that is also a very good. You are familiar with this. This is for the data communication. You can also refer this book for the line coding technique, Porogen. Okay, now we have to come to the next unit, that is we have to talk about the next unit, that is we have to be
Tawny. ते मामा कुठे ग? इंदुरीचे.
Please mute yourself. Okay, so this is the new unit that we have to be talking about, that is unit number 5, band pass digital signaling. Unit number 4, we have learned about the baseband signals. Now in this case we are going to learn band pass digital signaling. Okay, so in this case we have to go through certain topics, that is generation, detection, and signal space diagram of the amplitude shift keying, frequency shift keying, phase shift keying, quadrature phase shift keying, offset quadrature phase shift keying, QAM technique schemes. Okay, that is the quadrature amplitude modulation schemes, and these are the some binary schemes actually. Now, and at the end we would also learn about the A-Murray signaling, means more than the 2 levels we are talking about, that is MPSK, MFSK signaling, and finally the OFTM. Okay, these are the main topics that we are going to cover. So we have to cover. So if you have to see the band pass signal, we are talking about actually the digital to analog conversion, and these are the some main techniques that we have to follow for the binary signaling, that is amplitude shift keying, frequency shift keying, and PSK, that is a BPSK as well as a QPSK, OQPSK, and then quadrature amplitude modulation. Okay, so these are the some main techniques that we have to follow. So if you have to talk about that, first is the first technique that we are going to learn today is the that is amplitude shift keying. Okay, so first of all we have to see that why we have to be required for the modulation, why we have to be modulate actually. So in the digital modulation, it is a process by which digital symbols are transformed into the waveforms. Digital symbols means 0 and 1 would be transformed into the waveforms or the signals that are compatible with the characteristics of the channel. Because in the channel we can't directly transmit the binary numbers. We have to be required to transmit some voltage signals. Okay, so we have to first in the digital modulation, what we have to do? We have to convert or transform the digital symbols into the digital signals or the waveforms that is suitable to the or compatible to the channel. Okay, so in the case of baseband modulation, these waveforms usually take the form of the shaped pulses. Okay, but in the case of band pass modulation that we are going to learn in the unit number 5, baseband modulation we have already learned in the unit number 4, where we have to go through the PCM, delta modulation, like this. Now we have to in the case of band pass modulation, what happens? This shaped pulses, that is the digital shaped pulses, modulate a sinusoid, that is a carrier wave, and in this way we have to obtain the digital modulated waveform. Okay, so if you have to be talking about the radio transmissions, generally we have work on the radio transmissions. So carrier is converted into the electromagnetic field or electromagnetic waves for the propagation of the desired destination. Okay, so you have to see that sometimes this question would be asked that why is necessary to use the carrier for the radio transmission of the baseband signal. Can anyone answer me this? why is it is necessary to use a carrier for the radio transmission of baseband signal? Anyone has answer of this question? Why we have to be required to use of the carrier signal for the radio transmission of baseband signals? This kind of a question also asked in the interview as well. It is related to the size of antenna, but I have given you hint. You have to find out the answer. Next lecture I would ask this question again, and you have to find out the answer. This is your task. Okay. Now we have to come to our topic, that is the amplitude shift keying. Okay. So the binary ASK, it is a BASK is also called binary ASK, amplitude shifting system, was one of the earliest form of the digital modulation used in the wireless telegraphy. Actually, this kind of a techniques has been developed during the Second World War. There is a very good story has been mentioned in the book of the Top Sling related to that. We will discuss this when we have the in between of lectures sometime. So now you have to see that binary ASK system was one of the earliest form of the digital modulation used in the wireless telegraphy. And amplitude shift keying is a simple and elementary form of the digital modulation in which amplitude of the carrier sinusoid is modified in discrete manner depending on the value of the modulating symbol, depending upon the value of the message symbol. Actually, modulating means message signal. So in binary ASK system, binary symbol 1 is represented by transmitting a sinusoid carrier wave of fixed amplitude A and fixed frequency f0 for the bit duration of TV, where the binary symbol 0 is represented by switching off the carrier for TV segment. So in this case, for binary symbol 1, it is represented by a sinusoidal carrier wave of fixed amplitude A and frequency f0. But for the binary 0, it would be absence of the signal. Okay. So that's why it is also called as the on-off signaling, on-off shift testing. Because for binary 1, you would be turn on the switch, but for the binary 0, you would be turn off the switch. Okay. So both the frequency and phase in this modulation technique would be remains constant, only amplitude changes. This is the main feature of this particular course. Excuse me. So both the frequency and phase remains constant while the amplitude changes actually. So in this case, symbol 1 ASK signal can be generated by applying the incoming binary data and sinusoidal carrier to the two inputs of the product modulator. So what happens? We have to be symbol 1 ASK signal can be generated by applying a incoming binary data and sinusoidal carrier to the two input of product modulator. Here we have to use a switch, that is also called as a product modulator. And when you have to be mix the incoming binary data with the carrier signal, high frequency carrier signal, so it would be obtained a ASK waveform. Okay. So the ASK signal, which is basically a product of binary sequence and the carrier signal, has the same as that of baseband signal, but shifted in the frequency domain by plus minus f0. Okay. So it would be frequency and phase would be not changed, but it would be a little bit shifted practically because there is some practical limitations of the equipments are also there. It would be shifted little bit by the f0 plus minus, but actually only the amplitude of the signal would be modified. Okay. So you can see this waveform, that is of the ASK. You can see this is the first binary NRZ unipolar signals are there. That's why we have learned the line coding, because in this particular unit we would be use this line coding technique, the type of representation of the signals. Okay. That's why it is very important. That was a very important topic. So here we are using the NRZ unipolar digital signal, that is of the pattern of 1 0 1 1 0 1 0, like this. Okay. So and then it is a carrier signal, high frequency carrier signal. You can see the frequency of the carrier signal is very high, because you can see that in the one bit period of the signal, binary signal, there is a 2 cycles has been completed, or maybe that more than 2 cycles it is also possible. Okay. So we would be use a high frequency signal like that. We have already learned this in the practical also. If it is having a binary sequence having the frequency of 1 kilohertz, so it would be having carrier signal would be having a 20 kilohertz. Okay. So from that we have to be see that the amplitude of the only carrier signal would be modified according to the characteristics of the modulating signal, that is a binary sequence. So wherever the binary 1 is there, there is a presence of the carrier signal. Where is the binary 0, there is an absence of the signal. That's why it is also called as a on-off shift keying technique as well. So take this screenshot of this diagram, that is very important to understand the concept of the ASK. Okay. It is a very simplest technique. As we move forward, the technique would be a little bit complex. Now, this is the block diagram of the ASK generator. You can see that NRZ unipolar digital signal would be applied as a message signal, that is applied to a product modulator or a analog switch. You can use, instead of product modulator, you can write analog switch. And then there is a carrier signal, high frequency carrier signal is also applied to this product modulator, and after this modification there is a modulation would be occur. ASK would be there, amplitude shift keying signal. Okay. And this ASK signal would pass through the band pass filter for band limited ASK. It is not compulsory, but for the band limited ASK we have to be pass it through the band pass filter. Okay. So in this way we have to be generate the ASK signal. This is the basic block diagram of the ASK generator. Okay. Now I hope all of you have drawn this diagram. It is very simple. Now we have to be see that how we can mathematically represent the ASK signal. Okay. So it is also very important. In all technique we have to be learn the mathematical equations. That is also very much important, and you have to be noted down and remember this. This would be required to write in the paper. So let sinusoidal carrier can be represented by what? St is equal to A cos omega naught t, that is A is the amplitude, maximum amplitude of the signal. It is sinusoidal signal, that's why cos omega naught t, or you can write it as a cos 2 pi f naught t. Omega naught could be written as a 2 pi f naught. Then where the A is the peak value of the waveform, and the binary ASK signal can be represented by the wave St given by St is equal to A cos 2 pi f naught t. Only the amplitude is modified. We know that according to the value of the incoming binary signal, rest of the things would be same. So binary ASK signal can be represented by, also you can represent convert this particular point. A is what? It is a peak value of the signal. So we know that how to represent the peak value. Suppose this is the sinusoidal signal. Okay. And what is the A means here? A means is amplitude. This is the amplitude, maximum amplitude of the signal. This is your A. Okay. This is your A. But you can this is the peak value of the amplitude of the signal. You can represent in another form, like we know that what is the relationship between the A RMS signal. So you can see here A RMS would be equal to what? It would be equal to maximum amplitude, means AM or A whatever, upon root 2. Okay. So that is written here, correlated with terms. A is equal to root 2 A RMS cos omega naught t, or root 2 A RMS cos 2 pi f naught t. Okay. So ST is equal to 2A RMS square. You can also this is just a role of the representation only. We have taken the whole square root, so you can also write like this. Okay, square root 2 A RMS square cos 2 pi f naught t. Why we have written like this, we have to be see further the importance of that. Okay. Now from this point we have to be assume that these signals would be either a voltage signal or a current signal. Okay, waveform. So therefore you can represent the RMS value of the voltage signal in terms of power. Okay, RMS value would be represented in terms of power signal. So we have to be convert now voltage signal into the power form. So assuming this signal to be voltage or current, A RMS square would be represent the average power P. Therefore, PS is equal to what? A square upon 2, that is A RMS square. So you can also like write the amplitude shifting signal ST as in terms of power terms, that is square root of 2 PS cos omega naught t, or square root of 2 PS cos 2 pi f naught. Or you can also represent in terms of replacing the power, that is in watts, by the energy signal, that is joules per second. So this is another representation, that the relationship between the power and energy is that S upon T is the power. Okay, so that is and TB is the bit period actually. So these are the different representation. Actually, I have not written the equation number. You can give the equation number as well. Okay. So these all are the very important equations to represent the ASK signals. So everyone please note it down. So if you have to be go through in this way, maybe there is a 5 equations would be we have written here. You can give the number of equations as well. Okay. Now we have represented the ASK signal in terms of voltage form or power as well as the energy form. Okay. This would be help you to draw the constellation diagram or signal space diagram. So when you have to be going to draw the signal space diagram of the ASK waveform or the equation, for the symbol 1 can be represented as what? That is ST. We have now converted the energy term into the power form. Okay. So ES upon TB is the energy term. Now PS into TB is the, that is same term. So we have just multiply and divide the root square TB in the numerator and denominator here, and you have to be see that ST would be now written as root and square root of the PS TB phi 1 T. So what is the phi 1 T? Phi 1 T is the square root of the 2 upon TB cos 2 pi f naught T. Represent the orthogonal carrier signal. It would represent the orthogonal carrier signal. Okay. So we have extract the term of the orthogonal carrier signal from the mathematical representation equation of the amplitude shift keying technique. Now this orthogonal carrier signal would be helpful for drawing the signal space diagram for binary symbol 1 and symbol 0. So we are talking about a symbol 1 because symbol 0 there is absence of the signal, so it is not required to use here. That's why it would be only represent on the one axis. If it is binary 0 is also present, then it would be expressed in the orthogonal axis also. So the signal space diagram will be have the 2 points on the phi 1 T. One would be at 0 because for the binary 0 the absence of the signal, and other will be at the amplitude of the square root of the PSTB. Okay, so these are the amplitude of the signal, and the distance between both of the point would be 0 and square root of the PSTB is the called the Euclidean distance. So D is equal to square root of PSTB minus 0, that is same value, or either you can write it in terms of energy terms square root of the ES, and it is called the Euclidean distance. So for when we have to be drawing the signal space diagram, or also it is called as a constellation diagram. So we have to be always use the term Euclidean distance. Okay, so you can see in the diagram as well. I have written the shown the diagram that it is a x-axis and y-axis. In the x-axis we have represented the orthogonal signal phi 1 T, and so one of the point is at the binary 0 is at the 0 level, S0, and S1 is the for the binary 1, that is E square root of the ES or square root of the PSTB. And the distance between both of them is, if you have to see the distance is, this is nothing but D. Is that is the Euclidean distance is here. It is your D. Okay. Now everyone note it down. This is a very important term. Simultaneously, you have to be now start the attendance because these 3 minutes are only left. Okay. Now, those who I hope all of you have draw this diagram. Now we have to move to the receiving side or demodulation process. So when you have to come to the ASK demodulation process, you would be find that ASK demodulation can be done in two ways. There is a two ways. Therefore, one is the coherent detection, that is synchronous demodulation. Another one is the non-coherent detection, that is asynchronous demodulation. So what is the coherent ASK detection is that in this way, or synchronous, in this way of modulation process, demodulation process, the carrier signal which we are using at the receiving stage or receiver stage is in same phase with the carrier signal which we are using at the transmitter stage. And it means that carrier signal at the transmitter and receiver stage are of the same value. Okay. And this type of demodulation is called as a synchronous ASK detection or coherent ASK detection. So for applying the coherent ASK detection, we have to be tried to synchronize the carrier signal that we have used at the transmitter as well as we are going to use in the receiver section. Because at the both the end, we have to be required a carrier to modulate the binary signal into the ASK and to demodulate the ASK into the again binary one. Same carrier is required. So this is the block diagram of circuit diagram, we can say, for the coherent ASK detection. So you can see here at the receiving end, it is a noisy version of binary ASK would be received ST, and that would be applied to a multiplier, and where another signal would be that is a coherent carrier signal. Here, this carrier signal is locally generated at the receiver end, and it would be generated by taking the knowledge of the carrier signal at the transmitter end, and both the carrier signal having the same frequency, okay, same phase and same amplitude. So it would be again square root of 2 ps cos 2 pi f naught t. That's why it is the same value. And when both would be mixed to in the analog modulator, and this is the multiplier section, you would be obtained a signal that would be further passed through a you can say integrator, that is a low pass filter actually, that is having some bandwidth, and then this signal would be passed to the decision device where there is some threshold value of the signal would be set, and that would be decision device is nothing but a comparator actually. Okay, analog comparator, we are using the op-amp as a comparator. So output of the LPF low pass filter would be passed through the sample and hold circuit, and then it would be one of the terminal of the it would be this signal, and another is the threshold value, and finally you have to detect the binary signal. Okay, now time is very less. We will be continue this topic on the next lecture. Thank you all of you for attending the lecture. In the next lecture, we will also learn the BPSK. Thank you.